Right, section 7.4, dot product of algebraic vectors brings us to more dot product calculations, this time doing dot product formula when we're given algebraic vectors, so vectors by components in this case, right? The formula for this is a very simple calculation. We take the x components of both the vectors, multiply those together, take the y components of both of the vectors, take the z components of both of the vectors, multiply each of those partial products together, and then add the string of constant numbers. It's still a scalar, right? Dot products are always scalars. It generates a scalar. So here's the first example. Really easy work here. So a dot b is going to be -1. Oh, sorry, I shouldn't. It's not -1. I didn't look at this closely enough. Okay, so it's +1. I'll have to copy the vector statement here. So a vector is 1, -2, and 0. And I'm going to dot that with the vector 0, -1, and 2. So I take the 1 out of the x component, multiply it by the 0 out of the x component of the second vector, add that to -2 and then -1, that's this point and this point, and then add that to my 0 and my 2, and that's these 2 points as well. So that's just x components, y components, z components. I get a sum total of 2. Okay, so my dot product of two algebraic vectors, a and b, happens to be 2 here. Very easy. It works really nicely, and actually it's an easy calculation if I've got a couple of zeros in here. So if ever given the choice of picking arbitrary vectors, choose as many zeros as you can, because the following operations just make all those calculations quite easy. Okay, angle between two vectors. Same formula. We saw this in the last chapter. I need to find the angle between these two vectors when I post them tail to tail. So really, I don't think the diagram really matters. Okay, so this is the situation I'm going to do here. I'm going to have this as A and this as B, and that's what I want to try and find. So let's take the dot product first. Okay, since we've been practicing this already. Okay, on algebraic vectors. And I don't have to write all these steps. I know I always do when I first start this, but that'll be 1, 0, plus -2, -1, plus a -1 and 2. So I get a string of zeros, 0, plus 2, and a -2. So I've got 0 here. Okay, I should find what's the next part of the formula that I need? Magnitude of A. That'll be 1 squared plus -2 squared. That's just the individual components. I get this to be 4, 5, 6 root 6. And magnitude of B will be 0 squared plus -1 component squared, and then a 2 squared, all the square root, and I've got root 5. So my the angle formula, okay, just rearranging the original dot product calculation, that's A dot B over magnitude of A, magnitude of B. We got that to be 0 over root 6, root 5. This is 0, and cos theta is 0. That means it's 90 degrees. This example is a little different. Maybe we jumped a little bit too early in this. Most of the calculations will be non-right angled calculations, but this is an important example here. And I could have stopped right here. This is the point of this example here. I could have stopped right here. When the dot product is 0, that means the numerator, right? The dot product is in the numerator. The numerator is 0, and when the numerator is 0, okay, we know the whole expression is 0, and the cos of theta, the angle theta, when the cos theta is equal to 0, the angle is 90 degrees. This basically means, okay, that they're perpendicular. Okay? And anytime we get situations like this, when the dot product is 0, or the angle between the two vectors is 0, please make the conclusion that the two given vectors are perpendicular. Avoid a little bit of work, and we can just jump to that conclusion right away. If we're told in a question that the two vectors are perpendicular, please make the assumption, and again, it's not an assumption, it's a logical first step, that the two vectors dot product is 0, like the product of the dot product of the two vectors, when it's told that they're perpendicular, is in fact 0 here. Okay, let's work on this one here. I'm just going to pause this for a second and get started on it. Okay, let's find the angle between two unit vector combinations here. So I'm going to write as components. Okay, so that'll be -1. So it's I, J, K, right, in alphabetical order. I, J is 0, and K is -2. I've got to get my pen here going again. And then vector B, okay, is I, J, K. So I would be 0, J would be -2, and K is 1. So maybe we could find the magnitude now, the magnitude of both of them, okay, and then find the dot product of both of them. And I'm going to leave you guys to do that. I'll get back to you when the calculations are done, and then we'll go and find the cos. Okay, so magnitude of A, okay, is 5. Okay, that's -1 quantity squared plus 0 squared plus -2 quantity squared, all the square root of that. And similarly, we've got a √5 here. When the components are the same, that's fine. A dot B, okay, will be 0, -1 times 0 is 0, 0 times -2 is another 0, and then -2 times 1 is -2. So we've got cos of theta then is A dot B over magnitude of A, magnitude of B. That'll be a -2, and then I've got √5 times √5. I know that to be √25 or 5, right? Therefore, theta I've got down to be, I'm going to need my calculator for this, I think. Oh no, I've got theta to be 113.6 degrees here, if I've done that correct and right here. All right, so that's how we do that type of question. Okay, I'm going to transfer to the whiteboard, and I might as well, while I'm at it, do the other one on the whiteboard. These will take a little bit of time, so you can get started on A, and we'll get to it here in a second. Okay, so here's angle A in this question, and we'll call that theta, and I need AB. Now I have the components, right? So let me just size this down a little bit. I have the components, so vector AB will be 1 take away 0, so it'll be the vector 1, 0 take away 1, -1, and 2 take away 2 is 0 here. And while I'm at it, I might as well calculate the magnitude of vector AB. That's a really easy calculation. There's just a 1 and a 1 here. Okay, similarly, let's do AC. AC, so I start at A and I end up at C, so I'm taking -1 take away 0, that's -1. 2 take away 1 is 1, and 0 take away -2 is -2. And magnitude of AC, okay, it'll be 4 plus 1 plus 1, so our √6 here. That's a fast way to do these calculations. Okay, let's do our dot product. Let's write it like this. Okay, we'll do, so this will be AB dot AC divided by magnitude of AB, magnitude of AC. So I've got my two vectors, that's 1, 0. I'm going to dot that with negative 1, 1, and negative 2, and then divide that by root 2, root 6. Okay, that means I've got cos theta equals, I've got a negative 1 here. I'll do this all in one full swoop. 1 times negative 1 is negative 1. Negative 1 times 1 is a positive negative 1. And then I've got a 0 here, and that's over square root of 12 if I like. And cos theta then is negative 2 over square root of 12. Or if I do my inverse cosine, I get 125 degrees. Okay, and that's my angle between those two vectors. Okay, and that's kind of what this looks like here. So, for given points of a triangle, we need to find the vectors that make up the sides, find the magnitude of the side, find the dot product, work through the cosine formula calculation to find the angle between the two vectors. I think a homework question involves finding all three angles. So just do this basic operation for 2 of them, and then to find the third one, you can subtract the 180 from the first 2 calculated ones. Okay, I'm going to get back to the next question and pause this, and we'll get working. Okay, the next one appears to be a pretty easy question. Okay, but there's a lot to this going on here, and we've got to understand this first before we just jump right into it. So I want to find the angle between the given vector A, and this given vector A as a component is negative 2, 1, and 3. And find the angles that it makes, this vector makes with each of the coordinate, okay? So each of the coordinate axes. So if we have this coordinate axes, and there's all 3 of them, okay? You guys will get good at drawing this and visualizing this. Here's our vector. Okay, so negative 2, 1, and 3. So it's a vector that comes out about here. Okay, and I want to find the angle, okay, that A makes with the x-axis, and I want to find the angle that A makes with the y-axis, and I want to find the angle that the vector A makes with the z-axis. Okay, so there's a little bit of work here. Okay, so I've got A. I got to find magnitude of A. Okay, now that's 9 and 1 and 4, so that's square root of 14. Okay, and that actually applies to all of these. Okay, so we just have to understand the work that's involved here. Okay, and my vector A also is going to be the same. It's always the same. And magnitude of A, okay, is going to be square root of 14. Okay, my x-axis. Okay, let's use the unit vector 1, 0, 0. Okay, so that's the simple vector here, and that's going to be 1. Okay, my y-axis. Okay, now we've called these different things in the past, right? Okay, now that's I hat if I like, that's J hat if I like, and this can be my z-axis, and I know this to be IJK hat if I like, and this vector is going to be 1 as well too. So the calculation isn't that big a deal, really, when you understand exactly what we have to do. Okay, so let's go cos. Okay, so A. Oh. Okay, so then it's root I, and then I will do magnitudes here. So we've got, we didn't do dot product yet. Okay, so negative 2 times 0 times 0, all right? So negative 2, and in fact, if if I look at the x component, it's the x component that's always going to be part of that dot product here. Okay, so I've got root 14, root 1, which is really just negative 2 over root 14. And when I do the inverse cosine of that, I get my angle, according to my notes here. I don't see that I've ever calculated this. IJK. Oh, I've got 122. I better double check my calculation. Similarly, okay, if you see this pattern, so the angle that theta makes with the y-axis, okay, is going to be a k dot j over the magnitude of a, magnitude of j. Things really don't change. The dot product of a and j is really 0 times 1. Okay, 0 plus 1 plus 0. So it's always that was my point. It's always the y component. In this case, it was the x component. So it'll be 1 over root 14. And I have, according to my notes here, 74. I should carefully write this, okay, with some subscripts here, because I can't really use theta. Theta with the x-axis can be represented this way, or similarly, I could use 3 different Greek notations for this. Either way, I'm going to do it like this. Continue to do. So the next one will be theta. I'm going to call that z. And that'll be a dot k hat over a, magnitude of a, magnitude of k hat, and we've got 3 over root 14, or I think I've got, according to my notes, I'm going to verify those before we leave here. Okay, but that's okay, really the way we're looking at this. Now keep in mind, okay, that I want to make sure, okay, that remember our original vector was negative 2, 1, and 3, and the negative 2 is the x component, okay, and that shows up here on the x-axis. The 1 was the y component, that shows up here on the angle that the vector a makes with the y-axis, and then similarly 3 shows up in this case. So it's not a hard question. Definitely, it reads like an easy question. The calculations are quite easy, especially when we've got a bunch of zeros in here. When I do the dot product, it's an easy calculation. But there's a lot going on. We really have to understand that when I have a resultant vector like this a vector, it makes 3 completely unique angles with each of the x coordinates here. Now, if you really can see this and understand this, you can take this a step further. Okay, where the negative 2, okay, along the x-axis, negative 2, positive 1, and then out to the 3 units. Okay, and realize that if I have this resultant vector, okay, that the x-axis, okay, is going to be, okay, relatively large here. Okay, and that x-axis angle, okay, is going to be relatively a big size here. I am going to confirm some of these. Okay. Just before we go. Yeah, I got a 122 for that one. The next one, okay, so 1 divided by square root of 14, and then inverse cosine is 74, almost 74.5 degrees. And then finally, I'm going to go 3 divided by square root of 14, and then second function cosine is 36, almost probably better if it's 37 degrees. And there's no rhyme or reason. I mean, if I add all these together, okay, there's no connecting statement. It all has to do with the orientation of that vector A here. So that's how you do that, and that's it for, I think that's it for chapter 7.4. Let me just see if that's the case. Oh, we've got one more. We've got a few more here. I better get to that. Okay, so here's 2 vectors. A is the vector k minus 2, 3, and b is the vector 2, 2k minus 6, and 6. So I want to find out values for k that make these orthogonal. The term orthogonal is a little different. That means perpendicular when it's vectors. So I know when they're perpendicular, the dot product is 0. So I think I can probably find the dot product of these 2 two vectors. I think that's a calculation we should be okay with now when they're algebraic vectors. Okay, that's going to be 2k plus negative 2 times 2k minus 6. I got to work on that one. And then a plus 3 times 6 is 18. That equals 0. Okay, so I've got 2k minus 4k plus 12 plus 18 equals 0. It looks like I've got negative 2k plus 30 equals 0. Negative 2k equals negative 30. K must equal 15. Okay, so when k equals 15, okay, that would be the vectors. So A would be 15, negative 2 and 3, and B would be 2, and 2 times 15 is 30 minus 6 is 24, and 6. So these two vectors, okay, are perpendicular. Okay, so what happens when they're parallel? Okay, well, parallel, okay, the term here for parallel is collinear, when they lie in the same line. Okay, they're going in the same direction, right? So it needs to see if they're a combination of one another. So what I'm looking for is there a connecting scalar, okay, that allows me to do this to them. Okay, multiply b by any type of scalar, and I get a. So let's look at these vectors. Our first vector, okay, is a, k, negative 2 and 3, and our second vector is 2, 2k minus 6 and 6. Okay, so I'm going to do this a little differently than what I did in the past. Okay, is there any, each of the components, look at each of the components separately. Now, k exists in the x component in the first vector, and k exists in the y component in the second vector. Okay, I don't like that choice. Sorry, I'm going to change this variable. I've already used k, so I'm just going to change this. Okay, I better do that. Okay. Look at each of the components and see if there's an easy ratio that you can set up. Now, x isn't going to work, y isn't going to work because I'm going to have multiple variables here. But look at the z component here. Okay, my z components is 3 equals 6m. Okay, and if 3 equals 6m, clearly m, okay, is 1/2. So m equals 1/2 has to be my value here, okay, in order for this ratio to work. Okay, the only way 3 is related to 6 is through a factor of 1/2. So if you can solve one of the components and get that scalar constant, okay, then everything else follows from that. So what I mean is this: I've already solved for m. The only way this whole thing works is if m is equal to 1/2. Okay, so knowing that, okay, based on one of the components, really helps you solve this a lot easier here, and that should be 6. Okay, so now, okay, I can multiply the half into this. Okay, so that would be 2k minus 6. Oh, 2k minus 6, and then a half of 6 is 3. That should be divided by 2, and that should be k. Okay, so now right off the bat, okay, I can equate exponents here, and it looks like I've got k equals 1. Okay, and that's this one and this one here, equating the x's. So if k equals 1, I should also hold for my next one. Negative 2 should equal 2k minus 6 over 2. If I just found k to be 1, okay, does that work? Yeah, it does, doesn't it? Okay, so k equals 1, okay, satisfies, okay, this relationship. And when k equals 1, I know that these two vectors, okay, are parallel. Let's write that statement here. So when k equals 1, I've got 2. 2 times 1 minus 6 is, okay, is negative 4, okay, and 6. So look at that statement. Yeah, I mean, clearly we can see that and this vector are related, right, by a factor of m equals 1/2. Okay, so they're collinear. So really try and do these carefully, but quickly, and certainly understanding, okay, how this works. I'm just going to shrink this down a little bit, okay, and let you see both of these solutions, okay, as we work through this. I'll just pause it there and make sure that you're okay with that. Okay, last example, then some homework questions. Okay, so some dot product standard unit vectors. Our standard unit vectors are the vector I, okay, or I hat I call it, and that's the vector along the x-axis, 1, 0, 0. ij is next. That can be referred to as j hat, and that's the vector along the y-axis, 1, 0, 1, and then k, or k hat if you like. The hat symbol represents unit length 1, right? And that would be the vector 0, 0, 1. So here are the properties, and I'm going to confirm one. Okay, I'm going to confirm two while I'm at it here. Let's confirm I hat multiplied by our dot product of I hat. So that's going to be 1, 0, 0 times 1, 0, 0. Okay, and that'll be 1 plus 0 plus 0 equals 1. So the dot product of the two unit vectors along the x-axis is 1. And let's confirm another one just randomly. Let's go j dot k here. So that'll be 0, 1, 0 dotted with 0, 0, 1. So that'll be 0 times 0 is 0, 1 times 0 is 0, and 0 times 1 is 0. So I've got 0 here. These are interesting, okay, observations here, and something that we should be able to work through. What it means in practical Cartesian plane within 3 space really is for you guys to visualize and imagine here. I dot I is equal to 1, okay? J dot K is equal to 0. We'll save that for our analysis in chapter 8 of Cartesian planes. So enjoy. I thought that one was going to be a shorter one, but it wasn't, but that's okay. Enjoy the homework, and we'll get back to it in another